Students and viewers, you are welcome. In this video lecture, we are going to look at Math 101, and this course is called Set and Number System. Set and Number Systems. Number System. In today's lecture, we are going to look at this topic, and the topic is partial order relation. And partial ordered set. So let's start with what is a partial order relation. What is a partial order relation? Well, to begin, say a relation R defined on a non-empty set is called a partial order relation. If it satisfies the following properties. So the properties are these properties. So you see, we are talking about a partial order relation. First of all, it has to be a relation before you call it a partial order relation. A relation R on a set A is a subset of the Cartesian product A cross A. And we simply write this as a relation is a subset of A square. So this relation will be called a partial order relation if it has the following properties. 1, if R is reflexive, that is, for all A in A is related to A, meaning A is related to itself. 2, when R is antisymmetric, that is, for all AB in A, if A is related to B and B is related to A, this implies A is equal to B. All right. So the third one is transitive. If R is transitive, okay, R is transitive. That is, for all A, B, C in the set A, if A is related to B and B is related to C, then we have A is directly related to C. So an example of this relation, partial order relation, is the relation of being divisible on the set of integers. On the set of integers is a partial order relation. It's a partial order relation. So how do we check this? So to check this, say, okay, let's R be a relation on the set of integers given by, so that R is given by A is related to B if and only if and only if A divides B. So this is how we call this A divides B, or that B is divisible by A, or B is divisible by A. Okay, so if A divides B, and this is how we write it, remember, see, the integer A divides B if B is equals to AK, where K is an integer, also an integer. If there is a K such that AK is equals to B, then A divides B. So now let's check. So we have to check one, reflexivity. So we have to check if the relation is reflexive. So we all know, or it is clear, that every number, every integer, because we are in the set of integers here, every integer divides itself. What we are saying is that is for all A in Z, that's for all integer A divides A. And that is true because every integer can be written as A is equals to 1 times A. And therefore, A divides itself. And this is clear. So, and this implies that A is related to itself always by the definition of divisibility here as the given relation. So 2, anti-symmetric. Is the relation anti-symmetric? So now for all integers AB, so if A divides B, so if A is related to B, A is related to B, and B is related to A, clearly this implies, this means A divides B and B divides A. And what does that mean? An integer divides another integer, and that integer divides the first integer, clearly the two integers are the same. So we have A is equal to B. The two integers are the same. So 3, transitivity. So let A, B, C be integers such that A is related to B and B is related to C. B is related to C. This means that is by this relation divides, we mean A divides B and B divides C. Clearly, this implies that A divides C. We know that taking this as a simple example, just as a simple example, we have like now 2 divides 4, and 4 divides 8. We will have that 2 divides 8. So you see, by this relation, 2 is related to 4 and 4 is related to 8. Therefore, this implies what? That 2 is related to 8. And this is what happened here. So whenever a number divides another number, and that number also divides another number, so the first number divides the last number, and this is what we need. And so what? This also, by definition, A is related to C. And what is this? This is transitivity. And so the relation is transitive. And therefore, we conclude that the relation is a partial order. It's a partial order relation. So that if A is a set on which a partial order relation is defined, so then the pair, a partial order relation R is defined, then the pair AR is called a partially, so this is called a partially ordered set. So this is a partially ordered set to show that A is a set with a partial order defined on it. Example 2. This is example 2. We have defined what a partial order relation is, and we have given the first example as a partial order relation. But I think we need to give a counter example of a relation that is not a partial order relation. So the relation of being parallel to, so parallel. be parallel to, this symbol. We denote it by this symbol geometrically on the sets of all straight lines. Of all straight lines in a plane. It's not a partial order. It's not a partial order relation. It's not a partial order relation because at least the second property will fail. But let's see how it is. So this is defined by, you see, we define it by, let us define R by the line AB, for example. Line AB is parallel to line CD, or defined by line AB is related to line CD if and only if AB is parallel to CD on a plane. So now, the question is every line parallel to itself? Or you have so let K be the set of all straight lines. The set of all straight lines on a plane. And AB, CD. So an AB is an element of K. Now, is AB parallel to AB? The answer is no. A line is not parallel to itself because it lies on itself, and so it's not parallel. You see, reflexivity has failed. So AB is not parallel. Let me cancel the parallelism line. It's not parallel to AB. And so AB is not related to AB. At least if you check one example, if you check one property and see that it fails, actually you don't have to check all other properties. It is enough for you to stop there and say that the relation is not a partial order relation. But for the sake of being detailed, let's look at the second property, anti-symmetry. So suppose we have the line AB related to the line CD, and the line, okay, that is, the line AB is parallel to the line CD. Okay, the line AB and CD is parallel to the line AB. So, so what are we saying? We are saying AB is related to CD, and CD is related to AB. That is what we are saying. Parallel to is parallel to. So this is true always. But does that mean if you have AB is parallel to CD and CD is parallel to AB, does that implies AB equals to CD? So this does not implies AB, the line AB is the same thing as the line CD. Just because AB is parallel to CD and CD is parallel to AB, geometrically does not mean AB is equal to CD. And so this implies that equality does not hold. And by this not, we can say that is AB is not equal to CD. See, the second condition has failed. So at least if one of the three conditions fails, we conclude that the relation is not a partial order relation on the described set. Example 3. Consider consider the power set of a given set S. So now define a relation on the power set of S by, so a set S1 is related to a set S2 if and only if S1 is a subset of S2. So the relation we are talking about now is the relation of being a subset. So the relation of being a subset of a set between the power set of a given set. That is the relation of being a subset of that is the relation we are talking about. The question is R a partial order relation? Okay, let's check. It will be a partial order relation if it satisfies the given three conditions we have outlined in the beginning of our lecture. So we check 1. Reflexive. Is it reflexive? So reflexivity. Is it reflexive? Well, we all know that if you have a set A1 as a subset of a power set, it is always a subset of A1, meaning every set is a subset of itself. And so this relation is clear that A1 is related to A1, meaning A1 is related to itself, and so reflexivity hold. So let's check 2. The anti-symmetric relation. Is the relation anti-symmetric? That is, given that A1 is related to A2 and A2 is related to A1, what we are saying is, I will just say, okay, A1, this implies by the definition of the relation, A1 is a subset of A2 and A2 is a subset of A1, which clearly, from our set theory, we know that this implies that the two sets are the same. A1 is equals to A2. A1 equals A2. Once A1 is a subset of A2 and A2 is a subset of A1, and so we conclude that A1 and A2 are the same. So we see that the relation is anti-symmetric. The question we are to raise next, is it a transitive relation? So we check transitivity. Is it transitive? So, well, suppose A1 is a subset of A2 and A2 is contained in A3. See, what we are saying is A1 is related to A2. Let's use the relation first. And this is related, which implies by the definition of the relation, we mean A1 is contained in A2 and A2 is contained in A3. I mean, A2 is contained in A3. So clearly this implies that A1 is contained in A3, because a set A1, let's use a Venn diagram to describe that. You have, this is the power set of a given set S, or a given set A, for example. So you have this sets A1, A2 up to the last subset there. So you have A1 is contained in a bigger set. So this is set A1. This set is A1. And this set is named A2. And we have another bigger set, A3. So we say that A1 is contained in A2 and A2 is contained in A3. Clearly, A1 is already contained in A3. And this is what we have shown. And this means that A1 is related to A3. We are going to define what is a Hasse diagram. Hasse diagram. Now, what is a Hasse diagram? So we have a definition. A Hasse diagram diagram is a graphical, so it's a graphical representation of a partially ordered set. Partially ordered set. That is a POSET. It's a graphical representation of a POSET. So in this representation, so we write the arrow, the elements. So the elements of the set the element of the set are represented by nodes or dot or points. Nodes or points on the diagram or on the graph. 2, there is a line, that's a straight line from A to B, if A is related to B and B is placed above A. So B will be placed directly above A. Example, example 6. The relation of being divisible on the set A equals to 1, 2, 3, 4, 5, and 6, defined by A is related to B if and only if A divides B. So has the following Hasse diagram. So the Hasse diagram, we know that 6 is divisible by 3, so we put 3. And 6 is also divisible by 2, so we put 2. And these numbers are divisible by 1. So we write an arrow from 1 to 3. We write an arrow also from 1 to 2 to show that 2 is divisible by 1, 3 is divisible by 1. 6 is divisible by 3, so there is a direct arrow from 3 to 6. We have an arrow from 2 to 6. So this is a Hasse diagram for this relation divides. Or so this is a Hasse diagram. For the set A here. A together with the divisibility relation. So this is a Hasse diagram. Also for the relation less than or equal to on R of real numbers, or on Z of integers, Z plus positive integers here. So we can have the Hasse diagram. You can have the Hasse diagram as follows. So this is the Hasse diagram. So you have 1 is related to, so you see 1 is less than or equal to 2. So there is an arrow from 1 to 2. And 2 is less than or equal to 3. So there is an arrow from 2 to 3. So likewise 4. So and so on. This is how the Hasse diagram will be. So it will be just a straight line. Note that for simplicity, we have omitted transitivity. You see, there's an arrow from 1 to 3, there's an arrow from 1 to 4, from 1 to every other number, but because 2 is related, 3 is related to 4, and 2 is related to 3, so we have an arrow. We don't have to write an arrow directly from 2 to 4. So this is a Hasse diagram. For the relation on Z plus together with the less than or equal to relation. So now let's look at totally ordered set. Totally ordered set. So definition: a POSET, that's a partially ordered set. You have a set, you have a set A together with a partial order relation. So it's called a totally ordered set or linear set if, you see, the Hasse diagram is a linear here. Why? Because this is a totally ordered set. So if you see, for all AB in the set A, either A is related to B or B is related to A. That is, all the elements of A are comparable. Like in the set of positive integers that we have given example, you have 1 and any other number like 7, you see there is always a relation between 1 and 7. If you have like 7 and any other number 100, there is always a partial, there is always an order between 7 and 100. So for all A and B, either A is related to B or B is related to A. So there's always a relation between any other number. So every pair, what we mean here is that also that is every pair, so every pair of elements is related. Pick any pair, there is a relation in that on that pair. So example, the less than or equal to, the less than or equal to relation, this one, relation on R, the set of real numbers. Is a total order relation. Total order relation on R. It's a total order relation on R. And so R together with this relation is a totally ordered set or linear set. So this is example 6 or 7. So another example, example 8, the relation, at least we are now familiar with the relations, the relation of this being a subset of is not a totally ordered. It's not a total order relation on the power set of any set S. Why? Why is it not a total order? It's not a total order relation on any power set. It is not a total order because you can have two sets in a power set of a set. You can have two subsets that are not related entirely. For example, you have the power set. You have the power set of say P of S equals to, S is equals to a set containing 1, 2, and 3. So you have the power set of S as you have 1, you have 2, you have 3. So you have 1, 2, you have 1, 3, you have 2, 3. So this is a power set of that set. This is the power set. But you will notice that Notice that at least if two are not comparable, then the set together with that relation is not a total order. So look at it. The set containing 1 and 2, this is not a subset. None of them is a subset of the other. And 2 is not a subset of the singleton set 1. Likewise, 1 and 3, they are not a set. The singleton containing 1 and the set containing 3 are not comparable in any way. And so they are not comparable and they are not related. Likewise, the set 1, 2, 1, 3 is not a subset of the set 1, 2. Likewise, the set 1, 2 is not a subset of the set 1, 3. And so they are not related so in any way. And therefore, this relation is not a totally ordered relation. All right, thank you very much for watching our video. See you in the next video.